Howdy, I'm Yeaeun Lim in MEEN680. Today I'll talk about the basic optical principles behind thin film optical coatings. Instead of doing a literature review, I'll focus how they work visually. We'll see how simple interference effects in thin film can drastically change the reflection and transmission, and how this leads to anti-reflection coating, high reflector meters, and other useful devices. Optical coatings are made of nanometer-scale thin films deposited on glass or other substrates. By stacking materials with different reflective indices, we can tailor the reflectance, the transmittance, and even the phase at an interface. The most common types are anti-reflection coatings, high reflector meters, beam splitter coatings, and interference filters. When we specify a coating, we usually talk about its center wavelength, its bandwidth, and how sensitive it is to angle and polarization. In this talk, I'll focus mainly on the basic optical principles that make these coatings work. Let's start from the simplest case, a bare air-glass interface. Because the refractive index jumps from about 1 in air to about 1.5 in glass, a fraction of the light is reflected and the rest is transmitted. At lower incidence, the reflectance is given by this Fresnel formula. Plugging in the indices for air and glass gives roughly 4% reflection from a single surface. So a simple uncoated window already loses a few percent on each side and produces ghost reflections. The goal of many optical coatings is to reduce or control this Fresnel reflection. Now we place a thin dielectric film on top of the substrate. The incident wave is reflected at both interfaces of the film, so we have several beams that travel different optical paths. When they recombine, the phase differences between them produce constructive or destructive interference. The key quantity is the optical thickness n times d of the film. For many simple designs, we choose the optical thickness to be 1/4 of the design wavelength, so n times d equals lambda 0 over 4. In the next slide, we will see how this quarter wave condition leads to an anti-reflection coating. For a single layer anti-reflection coating, we set the film thickness to d equals lambda 0 over 4 nf. So the optical thickness is 1/4 wave at the design wavelength. The beam that reflects from the bottom interface then travels an extra half wavelength compared with the top reflection. That gives 180-degree phase shift. So the two reflective beams largely cancel each other. To make their amplitude similar, we choose the film index close to the geometric mean of air and substrate, which is NF, almost similar to root and air times and substrate. In practice, we use tools like the transfer matrix method to calculate the full reflectance spectrum versus wavelength and angle, but the basic idea is the simple destructive interference. If we repeat the quarter wave idea many times, we get a multi-layer dielectric stack or reg meter. We alternate high index or and low index quarter wavelength layers, typically written as HL, HL, and so on. At the design wavelengths, all of the interface reflection act constructively in the backward direction, so the reflectance can easily exceed 99 or even 99.9%. Common high-index materials include titanium dioxide, tantalum pentoxide, and niobium pentoxide, while silica and magnesium fluoride are popular low-index materials. For some broadband applications, simple matter films such as aluminum, silver, and gold are still used, even though they rely more on absorption than on interference. These interference coatings appear almost everywhere in optics. In lasers, high reflector and anti-reflection coating form the cavity meter and minimize loss. Thin film polarizers are also used in many ytterbium fiber and titanium sapphire systems. Dichroic filters separate excitation and emission light in fluorescent and Raman microscopes. Rugged broadband AR coatings are crucial for cameras, smartphone optics, and AR or VR headsets. Hot and cold meter coatings control the balance between visible light and infrared for lighting and thermal management. Finally, narrowband interference filters are used in LiDAR and satellite sensing to pick out very specific wavelengths. This is the reference, and thanks for the listening.